So the configuration and the type of heat exchangers that we have discussed so far is parallel flow heat exchanger and counter flow heat exchanger, right? These are the two configurations that we have discussed so far. And from the point of view of understanding the concepts, from the point of view of syllabus, from the point of view of any of the exams, these two types are most common. 99.9% these configuration only are asked and discussed. But if we talk about the practical applications of heat exchanger, there are more configurations possible, right? As we know already. For example, we can have a system where the flow is cross flow, means one of the fluid is flowing, let's say along north-south direction, other fluid is flowing around along east-west direction. So they are not totally aligned or not totally opposite in direction, rather they are perpendicular to each other, right? It's cross flow heat exchanger configuration. On a similar way, if you require even more heat exchange, then what you can do? Basically, heat exchange is occurring when both of them are directly or indirectly coming in contact with each other. They are exchanging heat, right? Suppose you have a system where you made the tubes which are having multiple passes through the shell or through the other chamber. For example, if we have one chamber, right now what do we have? That there is one chamber, one fluid is coming and exiting, right? And other chamber is, or other tube is passing like this, right? But what if, to ensure that good heat transfer rate is occurring, we have multiple passes, maybe we have two passes of the tube. So one pass of the tube and then we made it a U-turn, like many of our politicians. So we can take a U-turn and then it can flow along the direction of the shell once again. So rather than just having a single pass, it is having two pass, right? You can have 4 pass, 6 pass, 8 pass, depending upon how large the heat exchanger is or how much heat transfer you want to achieve. Generally, these are preferred in industrial usage. Industrially, in real usage of heat exchangers, you would find there are multiple passes of this tube through the shell. This is called as shell and tube heat exchanger because it is a shell, a bigger shell, a bigger covering, and this is the tube, right? So shell and tube heat exchanger, right? So these are some different configurations possible. In shell and tube also, as I told you, you can have multiple shells and multiple tubes. You can have 2 shell and you can pass the tube once again through the second shell, or through the same shell you can pass it 3 number of times, 4 number of times. There are many configurations possible depending upon, as I told you, practical application, depending upon industry. Because all of this, when you want to have a shell and tube heat exchanger, maybe you are having many tubes and many passes of those tubes. Obviously, these things take space and money, not only to purchase but also to maintain, right? Maintaining heat exchangers is also a task. So it should make economical sense to do all this. Economically, if you are spending money to buy and maintain it, it should make sense that the additional heat transfer rate that you are getting from this should be able to justify that cost that will go into the expense that will go into buying and maintaining the heat exchangers, right? So as I told you, in terms of concepts are absolutely same, and majority of the time, 99 out of 100 times, the heat exchangers that will be discussed are going to be parallel and counter flow heat exchangers. I am talking about syllabus and exam now. But whenever you get a question, suppose from the cross flow heat exchanger or the multiple pass heat exchanger, as I have shown and written here, right? Cross flow and multi-pass heat exchanger. How you need to solve the question? The basic concept is going to remain the same. Same thing is happening now. What is happening? Only the shapes are slightly changing, but ultimately basic concept is not changing. Heat transfer is occurring using the same principle and concepts as earlier, right? But one reality is that obviously if you want to find out the formulae, the expressions, those are going to get slightly complicated, right? So far, we have discussed one LMTD method only, right? When you will reach the next method, which is the effectiveness method, NTU effectiveness method, you will see that expressions there are slightly bigger, even bigger than this one, right? So right now you might be thinking, sir, expressions are easy, but as we will move forward, you will see they will get slightly complicated. So if we want to find out the actual expression, all the expressions that we have covered or we will cover for cross flow or multipass heat exchanger, analysis will get slightly complicated. To make the analysis simpler and easier to do, we use a factor which is called as correction factor. So as you can see from this diagram and from this diagram, that they are slightly complicated to look at, right? This is a shell and tube heat exchanger. This one is shell, the bigger container or encasing into which tubes are passing, and this is tube, right? You can see it can have multiple passes. It can have 4 passes, 6 passes, 8 passes. Many configurations are possible in this. You can have multiple shells also, as I told you. And this is the cross flow. As you can see, here it is flowing, one fluid is flowing in this direction, other is flowing in this direction, right? Both of them are neither parallel nor totally opposite, rather at 90 degrees. Here also if you look at it, this is the shell fluid which is entering here and leaving here, right? So it will be flowing like this. If it is entering from here and leaving from there, it will be flowing and exiting here, right or not? Focus on this part, only on this part, right? You can very clearly see that this and this and this, all of them are in the same direction. So it is like a parallel flow. But if you focus or if you look at this part, so this one and this one are in the opposite direction. On this side, the shell fluid is flowing in this direction, but the tube fluid is flowing in this direction. It is entering from here and leaving from there. So one side of the tube, this tube is having two sides. One side is acting like it's having a configuration like a counter flow heat exchanger. On the other hand, the other side is having a flow like a parallel flow heat exchanger. So these configuration, this one or this one, they are intermediate between parallel flow and counter flow. This one also, as we know, if both of them flow in the same direction, it is parallel. If they flow in opposite, it is counter, but it is 90 degree. It is not parallel, it is not counter. This hand is representing arrow. So if both of them are in the same direction, parallel flow. If both are opposite, it is counter flow. If it is perpendicular, then it is midway of same and opposite, no? Right? So this configuration is between parallel flow and counter flow. In a very similar way, here also you can see. It is neither a total parallel flow nor a total counter flow. The situation is in between them, right? So these heat exchangers, whether it is cross flow or multipass, they are a configuration which is between, not exactly midway, which are between, somewhere between parallel flow and counter flow. Conceptually, they are not different. Conceptually, nothing new is happening. Only shape we are changing, direction of flow we are changing. Conceptually, whatever we covered and understood about the parallel and counter flow will be valid for these two types as well. Even for all the configurations of these two types, not only these two. As I told you, there are many types of shell and tube heat exchanger. Multiple passes you can have, right? So the concepts will be same for all. But if you go on to find individual's expression, the expression for each of them, the expression can get slightly complicated. You might be thinking, sir, what expressions? Because in LMTD method, expressions are limited, right? We have not covered the complicated expressions yet, but in the next method, in the heat exchanger, in the next analysis, in the next method, we are going to cover NTU effectiveness method, where you will see some bigger and complicated expressions. So if you go on to write expressions for them, they will really get complicated. So they are not, discussed or asked any of such, they are not basically in our syllabus, in our discussion. But we can still analyze them using correction factor, as I told you. How can we do that? As I told you, these heat exchangers are somewhere between the counter flow heat exchanger and the parallel flow heat exchanger. They are somewhere between them. So the expression of LMTD and heat transfer that we have for counter flow heat exchanger, that we keep as a reference. Okay, for this discussion of these heat exchangers, we keep counter flow heat exchangers as our reference. And then we use a factor which is called as correction factor, which slightly modify the expression of counter flow heat exchanger to make them the expression of cross flow or multipass heat exchanger. That factor is called as correction factor F. Consider it to be just like any other discussion that we do. In a lot of subjects we have done that. If we have any ideal situation, suppose, and we want to talk about a real situation, real situations can be of different types, right? So we can use some factor, right? Some correction factor. Like we have done this one correction factor we have already used, where fluid mechanics, Bernoulli's equation, right or not? To differentiate between the real situations, what is going on in a viscous fluid, if you want to consider that, correction factor was used. So this is a similar correction factor which considers counter flow as its reference, and then we multiply the expressions and relations of counter flow with the correction factor to get the expression which will be true for a cross flow and multipass heat exchanger. That value of correction factor obviously will be different depending upon whether we have this type of heat exchanger or this type of heat exchanger, what are the temperatures. On 2-3 different factors it depends, mainly on 2 factors it depends, but that value will be different. That is our correction factor. So as I told you, the very first and basic way to define the correction factor is through LMTD, log mean temperature difference. As you can see here, that if you know the log mean temperature difference for counter flow heat exchanger, you have to multiply that with the correction factor and you will get the LMTD or delta T LM for the 2 heat exchangers, which is cross flow heat exchanger or multipass heat exchanger right? So this is the role of correction factor. It depends upon the configuration, on the geometry of heat exchanger and upon the inlet and outlet temperatures. Now let me ask you one thing here. Tell me what should be the value, general range of F. Think about it. As we already know that this value for counter flow is more than for parallel flow. This is something that we have already discussed, that this value for counter flow is more than delta TLM for parallel flow, right or not? So think about it. Look at this expression and tell me whether this value will be more or less than counter flow. Think about it. This is for those heat exchangers which are between parallel and counter flow. So if delta T, LM delta T or LMTD for parallel flow is less than that of counter flow, obviously the value of LMTD for them will be lesser than the counter flow now. If this value, parallel flow heat exchangers which have LMTD value less than counter flow, so from that logic, these also have the LMTD value, these also should have LMTD value less than counter flow, because they are a configuration which is between parallel flow and counter flow, which are not above counter flow, which are not better than counter flow, right or not? So logically their value should also be lesser than counter flow, and this is true. The value of LMTD, general value I am telling, I am not picking any specific case. There are exceptions here and there when phase is changing. We know that for phase change LMTD is equal for counter flow and parallel flow. Those are not the cases that we are discussing right now. We will discuss them. By the end of this discussion, I will tell you what will happen for phase change in these cases. But keeping those cases aside, we know that LMTD is highest for counter flow, lowest for parallel flow. And since cross flow or multipass are a configuration between parallel and counter flow, their value of LMTD also will be between parallel and counter flow, which is definitely less than counter flow. So if this value needs to be less than counter flow value of f also should be less than 1. Value of correction factor cannot be more than 1, otherwise this value will become more than counter flow value, which is not feasible because it is configuration between parallel and counter flow. So this is very much correct. The value of correction factor is less than 1 generally, but for certain limiting cases this value can be equal to 1 as well. We will talk about those cases. So f value range is not more than 1, and for limiting case its value is equal to 1. Now how do we actually determine the value of correction factor? We understood up to this point that yes, its value should be less than 1 for any general situation, but how much should be its exact value? How to find that out? So we have already done, for different configurations, we have already done our analysis and we have made certain charts. We have made certain chart. Similar to the case of Heisler chart. If you recall, for Heisler chart situation also, depending upon the configuration, whether it was a sphere, whether it was a cylinder, we were having different charts, right or not? In a very similar way, depending upon the type of heat exchanger, we have different chart with us. And those chart can help us knowing exact value of correction factor depending upon the configuration, depending upon the temperatures, inlet and outlet temperatures. These two things will help you to find out the exact value of correction factor. That value will be less than or equal to 1, but how much will be that value? That can be told by those charts. So what I told you, same thing I have represented here. The cross flow or multipass heat exchangers, they are represented as an inferior form of, as a downgraded form of counter flow heat exchanger, and the correction factor helps you in that. So this configuration, as you can see here, it is a cross flow heat exchanger or a multipass heat exchanger, but I have represented that into a form of counter flow heat exchanger only. Hot fluid is entering, TH in, hot fluid is leaving, TH out. Cold fluid is entering, cold fluid is leaving. If you look at them, this is flowing in this direction, cold fluid is flowing in this direction. Both of them are flowing in opposite direction to each other. But I have still written cross flow or multipass heat exchanger. Why? On the basis of correction factor, because I am not saying they are counter flow or they are counter flow. They are either cross flow or multipass, but only I have represented them in such a way because the basis, the reference for correction factor is counter flow only. They are not as good as counter flow. I am showing them as counter flow, but they are not as good as counter flow. They are slightly inferior, downgraded from counter flow heat exchanger. How much downgraded? That will be told by correction factor. So correction factor is coming here also, right? Generally, what do we have in the expression? Generally, what do we have in this expression? For any general situation, this is how heat transfer can be told for any general heat exchanger. When it is counter flow, this is how we can write it. And when it is cross flow, just multiply that with F, because the delta T for cross flow is equal to F multiplied by delta T of counter flow, right? So delta T is going to be defined exactly the same as we define delta T for counter flow, right? In the same configuration, this difference will tell you delta T1, this difference will tell you delta T2, right? I have written that here. Delta T, the expression of delta T for counter flow, LMTD for counter flow is this one, where the difference of TH in minus TC out is delta T1 and TH out minus TC in is delta T2. So the configuration looks exactly the same as counter flow. The expression looks, this is the expression of counter flow, exactly the same as the counter flow, having the same inlet conditions. Inlet conditions are same. So delta T counter flow in this expression is same as a counter flow heat exchanger with the same temperature conditions as this cross flow heat exchanger. But only in the expression of LMTD or heat transfer rate, we will multiply that with correction factor. So nothing is changing. If a question or discussion comes where inlet outlet conditions are mentioned, you will assume a hypothetical counter flow heat exchanger with the same inlet and outlet temperature conditions. Find out delta T1, find out delta T2, right? As I have shown here. find out LMTD, and then multiply that LMTD with the correction factor, and that will give you LMTD for that cross flow or multipass heat exchanger, and then you can use it to find out the value of heat transfer rate if required. Getting the point? As I already told you, the value of F will be less than equal to 1. You can write these 3 points down in your notes, right? The limiting value of F is equal to 1 is for counter flow heat exchanger, right? There are more cases when F can be 1. We will discuss them further, but you can very easily and simply say that when F is equal to 1, then this is counter flow heat exchanger, right? So it's direct theoretical question. It can be asked as a direct theoretical question. What is the value of correction factor for counter flow heat exchanger? So you don't have to think that for counter flow heat exchanger correction factor does not exist. You can say it exists. You can say that F is equal to 1. So whatever heat exchanger you are dealing with, that will be same as counter flow heat exchanger, right? So this is the limiting value of F for counter flow heat exchanger. Very easily we can say, as I have explained you in detail, that F is a measure of deviation of LMTD from corresponding value of counter flow heat exchanger. It tells you how much it has deviated, how much it has downgraded, degraded from counter flow value, right or not?